You are provided with solution J containing copper 2 ions, solution K 0.1 molar sodium thiosulfate, aqueous potassium iodide, solution L, solution N sodium hydroxide, starch indicator, and which is called solution M. You are required to determine the concentration of copper 2 ion solution J. The enthalpy change of reaction between copper 2 ions and hydroxide ions. Procedure. Using a pipette and a pipette feeder, place 25 centimeters cube of solution J in a 250 ml volumetric flask. Add distilled water to make up to the mark. Label this label this as solution J. Retain solution J for use in procedure 2. B. Place solution K in a pipette. Using a clean pipette and a pipette filler, place 25 centimeters cube of solution J2 in a 250 conical flask. Add 10 centimeters of potassium iodide, solution L. Shake well, then add 2 centimeters cube of starch indicator, solution M. Titrate until a blue-black color appears, and continue titrating until the blue-black color just disappears. So, what I'm saying is that this procedure is very important. You need to understand which solution is reacting with which one. Our table contains these values: 19.2, 19.1, 19.0. Let us take our initial to be 0.0 to 1 decimal place. 19.2, 19.1, 19.0. Calculate the average volume. The average volume, we can see we just add everything, so that is 19.2 plus 19.1 plus 19.0 divided by 3. This one will give you 19.1 centimeters cube. Calculate the number of moles of sodium thiosulfate used. Calculate the number of sodium thiosulfate used. Remember, we are given the molality of sodium thiosulfate. We have it here that 0.1 capital M. This is the molar sodium thiosulfate, meaning that 0.1 is the number of moles in 1,000 centimeters cube. That's what it means. So we say here that 0.1 is the number of moles which are in 1,000 centimeters cube. But we have used sodium thiosulfate solution K 19.1, so we will ask 19.1 centimeters cube will contain how many moles? What is 19? That's why you need to understand 19 is our volume, this volume here. Solution K is sodium thiosulfate. The volume, the average volume is 19.1. We want to calculate the number of moles in 19.1 sodium thiosulfate. So 19.1 times 0.1 divided by 1,000. So we will give you 0.0 191 moles. Calculate the concentration in moles per liter of copper 2 ions in solution J, given that the number of moles copper 2 ions in 25 centimeters cube of solution J are the same as the moles of sodium thiosulfate used. the number of moles are the same. Here I want you first to understand sodium thiosulfate reacted with J2 and not J1. What is J2? We took 25 centimeters cube of J and then we diluted it into 250 centimeters cube solution J2. We took 25 centimeters cube of solution J2, we reacted it with solution K, which is sodium thiosulfate. And we have been told that the number of moles of sodium thiosulfate reacted, which is in 19, is the same as in 25 solution J2. That's now fine. So we know that, so therefore moles moles of 25 centimeters cube solution J2 will be equal to 0.00191 moles. Why? Because the number of moles of J2 is the same as the number of moles of sodium thiosulfate used. We used 19.1 sodium thiosulfate, whose number of moles are this. Therefore, the number of moles is this. But remember, solution J2 was prepared and the volume was 250. So we have now moles in 25 solution J. We can get the number of moles of solution J2 in 250. So we say 25 centimeters cube of solution J2 equal to 0.00191. Then we will ask 250 centimeters cube of solution J2 will be equal to what moles? We multiply this times it divided by this. So that is 250 times 0.00191 divided by 25. This one will give us 0.0191 moles. Now we have the number of moles in 250 solution J2. But remember, we want the number of moles, concentration in J. Right? What is the relationship between J2 and J? Remember, we took 25 centimeters cube J, diluted this J to form J2, which is equal to 250 centimeters cube. Right? Therefore, it means the number of moles in 250, the number of moles in 250 solution J2 is equal to the number of moles in 25 centimeters cube solution J. Why? Number of moles does not change. Moles does not change. What changes is the concentration when you dilute a solution. Therefore, so this means that this is the number of moles in 250. Solution J2 will be equal to the number of moles in 25 centimeters cube solution J. 25 centimeters cube J as 0.0191 moles. Because we wanted concentration in moles per liter, we will ask 1,000, which is a liter. Centimeters cube solution J will contain which moles? 1,000 times 0.0191 divided by 25, which will give us 0.764 capital M. Capital M stands for molarity. Procedure 2. Using a clean burette, place 5 centimeters of solution N into each of the 6 test tubes. Using 100 ml measuring cylinder, place 20 centimeters of solution J in a 100 plastic beaker. Measure the temperature of solution J and record in the table below. To solution J in the beaker, add sodium hydroxide solution N from one of the test tube. Start the mixture with the thermometer and record in table 2 the maximum temperature reached. Continue with step D immediately. Add the sodium hydroxide solution N from another test tube to the mixture obtained in C above. Stir and record the maximum temperature reached. Continue adding the sodium hydroxide solution N from each of the other 4 test tubes, stirring the mixture, and record the maximum temperature each time and complete the table here below. So in a practical actually is to just follow the instructions. Understanding simple increase, that's okay, will help you to go. So let us see the values which we are supposed to use. When the volume was 0, the temperature, that is the room temperature, then was 22.5. After adding 1 test tube of, that is 5 centimeters of sodium hydroxide solution N, the temperature rose to 24.5. The temperature increased 26.5, 27.0, 27.0, 26.5, and then 26.0. So let us use this data to draw to plot our graph. We want to plot the graph, and then we shall see how to use the graph to answer the questions that are going to follow. Sorry. So I will draw my y-axis, and then my x-axis, I have been asked you to draw or to plot a graph of temperature vertical axis against the volume of sodium hydroxide. So against is the x-axis. So here you write volume of sodium hydroxide used. The volume is in centimeters cube. Here you write temperature because this is the temperature against. So here we write temperature in degrees Celsius. So by doing that, you have scored a labeling mark. And then let us now go to the scale. We know temperature does not begin at 0, but this one, our volume is going to begin at 0, and then 5, 10, 15, 20, 25, 30. Temperature, we will break this graph. We'll break it, and we shall start around 22, and then 23, 24, 25, 26, 27, 28. Now let us use our values to plot this graph. When the volume is 0, the volume is 0 here. So you need to check. When the volume is 0, temperature is 22.5. So 22. So here we have 0.5 at the middle. When the volume is 5, the temperature is 24.5. This is 24 and the 0.5 is here. When temperature is 10, when volume is 10, when the volume is 10, temperature is 26.5. When volume is 10, temperature is 26.5 here. When volume is 15, temperature is 27. 27 is here. When volume is 20, temperature is 27. When volume is 25, temperature is 26.5. 26.5 here. When volume is 30, temperature is 26. So having drawn like that, and you have seen that this is it is a graph that pertains to the topic of energy changes. Therefore, you understand the kind of line you are going to draw here. You draw a straight line. You can see this is an exothermic reaction. Its temperature was increasing and then decreased. Therefore, that one you should know. So let us draw this line here. Now look at this one. We have 3.1, 2, 3, We have 1, 2, 3, 4 points. So we take, they call them a line of best fit. So we take the line, if I take this one, this point, and this point, I will draw only with 2 points. But if I take this, and this, and this, I will draw with 3 lines, and that is now the best line of fit. So that's the best. So we are going to draw with this one. Yes. So once we have reached where we have the constant, we extend the line using dotted line. Extrapolate the line. We extrapolate the line. We extrapolate this line also until it meets that one. Very good. Now, where the two extrapolated lines meet, that is the maximum temperature reached, and we can get the volume of sodium hydroxide N used. So since we need the maximum temperature, we go to the temperature axis. We use this dotted, so it means our maximum is, this is 27.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 27.7. That's our maximum temperature. Using your graph, determine the volume of sodium hydroxide solution N that reacted completely with the 20 centimeters cube of solution J. So this is where we have the maximum temperature. So we go down to where we have the volume. So from maximum temperature, we go to volume. So to show that you used the graph, you must draw a dotted line from the maximum point where the two extrapolated lines met. You draw a dotted line down to where we have the volume, and then you see where this, at this point, this is what the volume, this is, remember, this is the volume. Therefore this is 10, this is 15. Therefore two small square represent 1. So this is 11, 12, 13, 14, and then 15. Therefore 13 is here. So the volume is 13 centimeters cube. We use this. So you have to show by using the dotted line. That's why they say from the graph. If you don't draw this dotted line, you won't score that mark. So the volume of sodium hydroxide used is 13.0 centimeters cube from the graph. We have done temperature change. So temperature, we must have maximum minus minimum. Our maximum was 27.7 and our minimum was 22.5. So you do that. Mathematics, you find it is 5.2 degrees Celsius. 5.2 degrees Celsius, that is our temperature change. Calculate the enthalpy change for the reaction per mole of copper 2 ions. Mark that, of copper what? Copper 2 ions. So we remember a mixture, we used a volume of copper ions and a volume of sodium hydroxide. But here they have specified that we want to calculate the enthalpy change for the reaction per mole of copper 2 ions. Very important to note. We know that heat change is equal to capital M, mass of the solution. It is capital M is the mass of the solution times specific heat capacity times temperature change. This one, this is the total volume. The total volume was 20 plus 13. This is the copper ions and this is the hydroxide. So we have 33 centimeters cube divided by 1,000. Remember, centimeters cube is the same as grams. Using this, we know we have done so many. So with density is equal to mass over volume. So if I have volume, I have density, I can get mass. So it is 33 grams times specific 4.2 times temperature change 5.2. Sorry. So you take your calculator and multiply all this, you will get 0.07 0.072 kilojoules. Correct? So, but one thing we need to know is the number of moles of copper 2 ions. The volume that we used for copper 2 ions is 20. We used 20 centimeters cube of copper 2 ions were used. Therefore, but we know the concentration of copper 2 ions from our previous calculation. We know the concentration of copper 2 ion solution J from the previous calculation. We know the concentration of J, which is 0.764. This is the number of moles in 1 liter. So we are going to ask if this is the number of moles in 1,000 centimeters cube, what will be the number of moles of 20 centimeters cube of the copper ions? So 0.764 moles are in 1,000 centimeters cube of copper 2 ions. We will ask 20 centimeters cube of copper 2 ions will give us which moles? This times divided by this, which will give us 0.01528 moles. So this is the number of moles of copper 2 ions that was able to produce this. So now we want 1 mole per mole. Enthalpy change. Remember, enthalpy change, it is per mole, per 1 mole. So we will say 0.01528 moles was able to produce this amount of heat, 0.07072 kilojoules. And then 1 mole will produce what amount? So it is 1 times this divided by 0.01528, which will give you 47.12 kilojoules per mole. Kilojoules per mole. But before you put your pen down here, you must remember, was the reaction exothermic or endothermic? The reaction was exothermic because temperature was increasing. Therefore, our answer is negative 47 point this. Therefore, it is negative 47.12 kilojoules per mole. The qualitative part of it, you are provided with substance P. Carry out the test below and write your observations and inferences in the spaces provided. Describe appearance of solid P. Solid P was white, so you just write white crystalline solid or substance. Whenever it is white, you just write white crystals. It is acceptable. White crystals. Place about 1/3 of the substance P in a dry test tube and heat it strongly. So you put it and heat it strongly. There is no testing of any gas. Just heat it, and then a colorless solution, a colorless liquid, actually, a colorless liquid condenses on the cooler part, in the cooler parts of the test tube. That simply tells you that this substance P contains water of crystallization. It is an hydrated salt. That one is acceptable. Or you say the salt contains water of crystallization. Contains water of crystallization. So either is acceptable. So if it was a crystal, and then another observation which you can make is that the solid will remain. What will be the color? A white solid remains. A white solid is formed or remains. There you don't need to make any inference. Place the remaining amount of solid P in a pouring tube. Add about 10 centimeters cube of distilled water and shake well. Retain the mixture for test D below. So this one, the solid, dissolve for me a colorless solution. That tells you that the colored ions are absent, and we know the colored ions, which is copper 2 positive, which is blue, ion 2, which is green, and then ion 3, they were absent because it formed a colorless solution, and this is blue, this is green, and this is brown. Therefore these ones were absent. It is also acceptable if you forget this one, you can write soluble salt present. You can say soluble salt present. It is acceptable. Use about 2 centimeters portion of mixture obtained in C for test 1 to Roman 3 below. So add 2 to 3 drops of aqueous barium nitrate. We are adding barium nitrate. We expect a white precipitate because barium will form a white precipitate with the sulfate, the sulfite, and the carbonate. Barium carbonate, barium sulfite are white precipitates. So what is the observation? White PPT formed. So a white PPT is formed. If a white PPT is formed, then it tells you that it is sulfate, the carbonate, the sulfite, okay, the carbonate, then the sulfite is present. Okay, add 5 drops of dilute nitric acid to the mixture above. So the mixture will dent. What will be the observation? We are adding dilute nitric acid 5 and then 5 drops. There is no effervescence. No effervescence. If there is no effervescence, we are adding in a dilute nitric acid, then it means the carbonate, the sulfite is absent, because this one, when you add an acid, they form a effervescence. They produce carbon dioxide, and this one will produce sulfur 4, which will produce effervescence. But this one, so it means that the carbonate and the sulfite are absent. But remember, from our previous, we had the sulfite, the carbonate, and the sulfate. Therefore, it means that the sulfate is present. Because if this one are absent, and in our previous Roman 1, we said the 3 were there. So this one are not there. What is it there? This one is present. Acceptable. It is acceptable like that. Add to the mixture aqueous sodium hydroxide droplets until in excess. We are adding sodium hydroxide. The observation is that white PPT is formed. White PPT is formed, which is insoluble in excess. A white precipitate insoluble in excess. So that tells you, we know that what that it means. When adding sodium hydroxide, a white precipitate is formed insoluble. Then we know for sure that the barium, the calcium 2 positive, and magnesium 2 positive are there. Yes, we know that the barium 2 positive calcium are present. But now this is our last test. We are going to ignore the barium and the calcium, and then we are going to take the magnesium. 2 positive is present. Why do we ignore that? This one forms a white precipitate, which is white, very white. But when you look at this one, they form a white precipitate, but it is not that white. But this one, it forms a very white precipitate, so we just take it as the one that is present. So give the formula of the cation and anion present in the substance. So the cation is magnesium and the anion is the sulfate. The last part of it, number 3, you are provided with an organic substance Q. Carry out the following tests and record the observation and inferences. Place about 1/3 of substance Q on a metallic spatula and ignite it with a Bunsen burner. The observation is that it melts. Solid Q melt and burn with a yellow sooty flame. So if that happens, then you should know it is a double bond or the triple bond that is present. Right? Place the remaining amount of substance Q in a boiling tube. Add distilled water. Heat the mixture and allow it to cool for about 30 seconds. Divide the mixture while still hot into 2 portions. To the first portion, add solid sodium hydrogen carbonate. Then effervescence occurs. It's always observed. Effervescence is observed, then it means that is present. Alkanoic acid is present. You are provided with aqueous sulfuric 6 acid labeled solution A, solution B containing 10.4 grams per liter of potassium carbonate. This information is very important. So this one means it is 10.4 grams per liter, very important, of potassium carbonate. And then this one is for the next one. So you are required to determine the concentration of A. Procedure 1. Using a measuring cylinder, place 25 centimeters cube of solution A into a 250 ml volumetric flask. Add distilled water to make 250 centimeters of cube of solution. Label this solution C. Place solution C in a purette. Using a pipette and a pipette filler, place 25 centimeters cube of solution B into a conical flask. Add 2 drops of methyl orange indicator provided and titrate with solution C. Record the results in the table. I have already recorded the results. I hope and I know you know how to fill this table. It is important you consider or you ensure that the decimal point is 1. You use 1 or 2 consistently. but it is okay for you to use 1. The arithmetic kusubtract hii 9.5 minus 0, you should ensure here everything is written correctly. However, what's happening here? And so we have started revising for 2024 exams. In fact, it is important you start earlier. Ukingoja kuja kuanza September, you will lose hope. So what is happening here? We are taking 25 centimeters cube of solution A, diluting it in a 250 volumetric flask, and forming a solution 250 centimeters cube of solution C. Solution C is a solution of A. The difference is that it has been diluted. A is sulfuric acid. Very good. So is A, which is sulfuric acid, now we are going to use our C. C, sulfuric acid diluted, is going to react with B. And what is B? B is potassium carbonate. So this is a carbonate with an acid. You should know that equation, how to write that reaction. It is a base, a carbonate plus an acid. So let us go to the question. Calculate the average. So average, you just write 9.5 plus 9.4 plus 9.4 divided by 3, which is equal to 9.43. The average is always given to 2 decimal places. The average, make sure you always give to 2 decimal places. Question 2. Calculate the concentration. The question starts here. Calculate the concentration of potassium carbonate in solution B. So we want now to calculate the concentration of solution B. What do we have about solution B? Solution B contains 10.4 grams in 1 liter. So there are 3 very important triangles in titration. So I want to use this one. We have one here. Remember, concentration in moles per liter is what we call molarity. It is important to know what is molarity. Molarity is the number of moles per liter. The number of moles in 1000 centimeters cube of solution is called molarity, and is called concentration in moles per liter. So this one is the same as concentration in moles per liter. So whenever you are asked to calculate the concentration in moles per liter, it is exactly equal to molarity. So now I have a table here. So let's say that molarity is equal to, so from here, molarity is equal to mass in grams per liter divided by RFM. We want to calculate the molarity or the concentrations in moles per liter of potassium carbonate. Potassium carbonate is written as K2CO3. That is very important. You should know how to write the chemical formulas. If you make a mistake here, it means you are going to get the wrong RFM. So you have been given the relative atomic mass. Carbon is this, oxygen is 16, potassium is this. So what you do, you just add potassium, that is 39, times 2 plus carbon, which is 12, plus 16 times 3, which is 48, and it will give us a total of 138, and that is the RFM of potassium carbonate. Now, because tuko na RFM of potassium carbonate, lakini tunataka molarity is equal to mass in grams per liter of RFM. We were given the mass of potassium carbonate in grams per liter. So we just bring it here. Say now, molarity is going to be mass, which is 10.4 divided by 138. And this one gives us 0.0 0.75 for capital M. Capital M stands for molality, and the molality is the number of moles in 1 liter. Question 3. Calculate the concentration of sulfuric acid in solution C. In other words, what is missing here? Concentration is in moles per liter. That's very important information that is missing here. So calculate the molality of solution C. So tutapata aje molality of solution C? Kwanza tunajua solution C ili react na potassium carbonate. Tushapata molality of potassium carbonate. So hapo ndio tunaanza. First, write the equation of the reaction that took place. The reaction was between potassium carbonate, which is now solution C, solution B, so reacting with sulfuric acid, solution C, very important to note. So this one will form potassium sulfate plus carbon 4 plus water. Right? We don't care about writing the status first. What we want is to write an equation that is balanced, because there is a relationship between this and this, so we need to check, is the equation balanced? If the equation is balanced, that's okay. The equation is balanced. It means the number of moles that reacted with the number of moles of potassium carbonate that reacted with sulfuric acid are equal. So we start here. What do we know? We know the molality of this one. We know the volume of solution B that was used. So the solution B, you were told that using a puree pipette 25 of solution B, we know the volume of solution B that was used. Well, right, that one we know. So, but what we know is that molality is the number of moles in what? In 1,000. Therefore, this moles here, 0.0754 is the number of moles where? In 1,000 centimeters cube. Because I have told you molality is the number of moles in a liter. A liter is equal to 1,000 centimeters cube. So tunauliza what was the volume of B? Remember, this is solution B. What was the volume of B that we used? We used only 25 centimeters cube. Will it be how many moles? So that one will be 25 times 0.0754 you divide by 1,000. This one will give us 0.00185. So this is the number of moles of potassium carbonate that reacted with sulfuric acid, this volume. Remember, the volume of sulfuric acid, the solution C, is 9.43. So 25 centimeters cube of B, potassium carbonate, reacted with 9.43 solution C, sulfuric acid. Hapo tuko pamoja. Very good. So now here we are here. The mole ratio here is 1 to 1. Kwa sababu ukiangalia hapa ni 1, hapa ni 1. So the mole ratio is 1 to 1, meaning that the number of moles of potassium carbonate will be equal to the number of moles of sulfuric acid C, solution C. Very nice. So moles of C, which is sulfuric acid, will be equal to this because the ratio is 1 to 1. So will be 0.001885 moles. Very important. Now the next thing we know is that the volume of C that reacted with the B is, the volume is the average 9.43. This is the volume 9.43. So we ask that this number of moles, 9.43 centimeters cube, solution C contains 0.001885 moles. The question asks us concentration in moles per liter. In other words, they are asking for molarity. So what do? You ask molarity is the number of moles in 1,000. You ask here 1,000, which is a liter, centimeters cube. Solution C will contain how many moles? Now that one will be 1,000. Will be 1,000 times 0.001885. You divide by 9.43, right? And this one gives us 0 will be 0.1999 molar. So this is the number of moles of solution C in 1,000. Tunaelewana? In this question, the only thing that is missing here is concentration in moles per liter. Concentration in moles per liter. Concentration in moles per liter. Remember that. So let us look at the last question. The last question asks us to calculate the concentration of sulfuric acid in solution A. Remember, solution A is the original sulfuric acid. We took 25 centimeters cube of A, tukaiweka kwa volumetric flask, tuka add water ikafika 250 centimeters cube, tukaita hiyo solution C. Ni sulfuric acid lakini yenye tulitoa kwa A but iko diluted. So what is very important here is for you to know that the number of moles in 250, the number of moles in 250 centimeters cube solution C will be exactly the number of moles in 25 centimeters cube solution A. Did you get that? Let me repeat that. Very important. The number of moles in 250 centimeters cube, the diluted solution C, will be exactly equal to the number of moles in 25 centimeters cube of solution A, the one we diluted. So that is very important. But from here, we know that the number of moles of solution C in 9.5 is this one. Fine, if we even know the molarity, so we can use N. So we are going to say that, now let us get the number of moles of solution C in 250. We will just use this one here, that 9.43 centimeters cube solution C has how many moles? 0.001, right? 885. So this is the number of moles of solution C in 9. So we will just ask 250 centimeters cube. C will contain how many? That is 250 times 0.001885. We divide by 9.43. And this one will give us 0.04997 moles. So this is the number of moles in 250 solution C, 250. Na nimekuambia kwamba number of moles in 250 centimeters solution, the number of moles in 250 centimeters cube solution C will be exactly be the number of moles in 25 yenye tulitoa tukadilute. So tukijua hiyo information, hapo umeelewa kabisa. So it means that 25 centimeters cube of solution A, moles zake ni easy, this one. So 25 centimeters cube solution A sulfuric acid contains which moles? This one, zenye ziko kwa 250 solution C. 0.04997. So concentration in moles per liter is the number of moles in a liter in 1,000. So we will ask if 25 is that 1,000 a liter centimeters cube, A will contain how many moles? So we will have 1,000 times 0.04997. We divide it by 25. and this one will give us 1.999 mole. This is the molarity of solution A, the original sulfuric acid. Thank you. Allow me to take you through this question. You are provided with solution J. Solution J is ammonium iron 2 sulfate solution, and this is the formula. Solution K is 0.2 molar potassium manganate 7 solution. You are required to determine the molarity of ammonium iron 2 sulfate, the amount of water of crystallization N in ammonium iron 2 sulfate, the formula mass of ammonium iron 2 sulfate. The procedure: the ammonium iron 2 sulfate solution provided was made by dissolving 8.5 grams of the salt in 50 centimeters cube of dilute sulfuric acid, and then making the solution to 250 centimeters cube using distilled water. So this is solution J. Fill the puree with solution K, pipette 25 of solution J, and measure and release into a conical flask. Titrate J against K until the solution becomes permanent ink. Repeat 2 more titration times. Repeat more times and complete the table below. Let me give you the value of the table. 22.1, 21.9, 0.0, 0.0, 0.0. This one is 21.9, 22.1, 22.0. Let us go straight and get the average volume. Calculate the average volume of solution K. So this is solution K, and remember solution K is potassium permanganate. So the average is 22 plus 21.9 plus 22.1 divided by 3. This one is going to give us 22 centimeters cube. Calculate the number of moles of solution K reacting. Calculate the number of moles of solution K reacting. Also, you need to understand how to be aware of solution K. So when you forget, you go back. Solution K is 0.2 molar potassium permanganate, meaning that 0.2 is the number of moles in 1 liter. 1 liter equal to 1,000 centimeters cube. So we ask here that 2 molar, 0.02 molar implies that 0.02 is the number of moles contained in 1,000 centimeters cube of solution K. 22, because the volume used is 22 centimeters cube, K will contain how many moles? So it is 22 times 0.02 divided by 1,000, and this one will give us 0.00044 moles. Determine, or given that the equation for the reaction is Given that the equation for the reaction is this, determine the number of moles of iron 2 salt solution J in 25 centimeters cube of solution used. Now, let us first interpret this here. The permanganate is what we call solution K. The iron is solution J. What is the volume of the iron used? The volume, we took 25 centimeters because we pipetted 25 centimeters cube. 25 centimeters reacted with 22. But K. Now we have the number of moles of K that reacted with J. The number of moles is this one, 0.00044. We can see that the ratio, the mole ratio is 1 to 5. So the manganese or the manganate ion to the iron, the ratio is 1 to 5. But we know the number of moles of this, which is 0.00044. So if 1 is equal to this, 5 will be what? That means it is 0.00044 times 5 divided by 1. So when we give us 0.0022 moles. Determine the molarity of solution J. Molarity. Like I've always said, what is molarity? Molarity is the number of moles in 1 liter. Molarity is the number of moles of a solution in 1 liter. So J, we know the number of moles of J in 25. This is the number of moles. What will be the number of moles in 1 liter? 25 centimeters cube. Solution J contains 0.0022 moles. 1,000, that is a liter cube. Solution J contains how many moles? That is the number of moles in 1 liter of J. Determine the concentration of solution J in grams per liter. Grams per liter. So J, how was J prepared? So you go back to the procedure and then you realize like this one. The ammonium ion, which is solution J, remember solution J is the ammonium ion, was made by dissolving 8.5 grams in 250 because the total volume distilled water plus this HCl will form plus 200 will form 250 centimeters cube because the volumetric flask of 250 will contain a volume of 250 centimeters cube. So 8.5 grams of the salt was dissolved, making a solution of 250 centimeters cube. We want mass in grams per liter. So concentration in grams per liter. So you ask 250 centimeters cube solution J was prepared by 8.5 grams of the salt, and then 1,000 because a liter is 1,000 centimeters cube. J will contain how many moles? 1,000 times 8.5 divided by 250. This one will give you 34 grams per liter. Next question. From the result in 3 above, 3C, this is C Roman 3 above, determine, this question is misplaced. the formula mass, which is the RFM. So it is supposed to be here. Determine the RFM of the iron 2 salt, iron 2 salt, hence calculate the value of N in the formula, this formula. So first we calculate the RFM. This question is just misplaced here. It was supposed to come before this one. So let us see how to calculate the RFM. There is always this triangle I will always give you. Molarity, RFM, mass in grams per liter. So once you have mass in grams per liter of a substance, you have the molarity of that substance, you will get the RFM very easy. So RFM is equal to mass in grams per liter divided by molarity. We are talking about the iron 2 salt. We have, which is solution J, we have the mass in grams per liter, which is equal to 34 divided by molarity. We have calculated the molarity of the solution, which is in Roman 2. We have calculated the molarity of the solution, which is 0.08 am. So 3.4 divided by 0.088, which is the molarity of the solution J. This one, using your calculator, you will get it is 386.4. So that is the RFM. But we know that the RFM is this of this formula. When you add each mass of each element, the mass of each element here, you will get this. So it means that ammonium, this ion, when you add everything here, you will get this 386.4. But we have been given N for nitrogen is 14. We have all the atomic mass of each element here. So this one is 14 times 2 plus hydrogen is 4 times 2 because hydrogen is 1, 8. Sulfur is 32 plus 16 times 4 is 64 plus iron is 56. Sulfur is 32. This one is 64. That is 16 times 4 plus, because this dot is a separation. Water is 16 plus 2, which is 18. 18 times this, it is 18N, which is equal to 386.4. Add everything here, you will get 284 plus 18N equal to 386.4. Like terms together, 18N is equal to, you subtract this here, is equal to 102.4. You divide it by 18, you find that N is equal to 5.688, which is equivalent to 6. So that is the value of N in this salt. Determine the correct formula for the ion. So the formula, we are going to replace N with 6. like that. You are provided with solution A, 0.5 molar sodium hydroxide solution. Solution B, 0.5 molar hydrochloric acid. Solid C, 2.2 grams of X2 carbonate. Methyl orange indicator. You are required to determine the relative atomic mass of X in this compound. Procedure. Fill the purate with solution A, sodium hydroxide solution. Measure 100 centimeters cube of solution B and put it in 250 centimeters cube beaker provided. Pour solid C slowly into a beaker containing solution B while stirring for about 4 minutes. Label this solution D. Pipette 25 centimeters cube of solution D into a conical flask and add 2 to 3 drops of methyl orange indicator. Titrate solution D with solution A until the endpoint is reached. Record your results in the table below. Alright, let us use this value. Let us use 8.5. We want to fill our table with 8.5. 8.5. Our initial is 0.0, 0.0, 0.0. When we subtract this one, we find it is 8.5, 8.5, 8.5. So our average, it is 8.5 plus 8.5 plus 8.5 divided by 3, which would give us 8.5 centimeters cube. And now, before we continue, it is important for you to know this. First, what is happening in this procedure? We are taking 100 centimeters cube of solution B, but remember solution B is what? Hydrochloric acid. 100 centimeters cube of solution B, that is the acid HCl, were reacted with C, solid C. So after reacting with solid C, some moles were used actually. Therefore, solution D is HCl. That's something which you must also, I want to understand. Solution D is HCl, yes. But which HCl? The excess, the one that remained after reacting with solid C. So it means that solution B was in excess, that is HCl was in excess. Some of the HCl reacted with solid C and some acid remained, which is now going to react with solution A, sodium hydroxide. It is important for you to understand that. So let us go to question B. Determine the number of moles of solution A, sodium hydroxide, that reacted. Now, the volume of solution A used is 8.5 centimeters cube. But a good thing is that we know the molarity of sodium hydroxide. Solution A is 0.25 molar, meaning that 0.25 is the number of moles in 1 liter in 1,000 centimeters cube. What will be the number of moles in 8.5? So we ask that 0.25 is the number of moles which are contained in 1 liter. 0.25 is the number of moles contained in 1,000. Remember, 0.25 capital M implies this. Implies that 0.25 is the number of moles in 1,000. Now we will ask 8
0.5 centimeters cube will contain how many moles? So it is 8.5 times 0.25 divided by 1000. This one is going to give us 0.0022125 moles. That is the number of moles in solution A used, the one that reacted with D. Yes. Calculate the number of moles of hydrochloric acid in 25 centimeters cube solution D. Correct. We want to calculate the number of moles in 25. Remember D, which is HCl, reacted with A, sodium hydroxide. Meaning because HCl and sodium hydroxide is the ratio, mole ratio is 1 to 1. Therefore moles of 25 centimeters cube D equal to these moles, 0.002125 moles. The reason the ratio is 1 to 1. Calculate the number of hydrochloric acid in 100 centimeters cube of solution D. Calculate the number of moles of hydrochloric acid in 100 centimeters cube of solution D. Now we have the number of moles of solution D in 25. We got that one. This is what we got in our previous Roman 1. So we ask 25 centimeters cube solution D contains 0.002125 moles. 100 centimeters cube solution D will contain how many moles? So it is 100 times 0.002125 divided by 25. This one is going to give us a 0.085 moles. 0.085 moles. Calculate the number of hydrochloric acid. Remember, we are using this question. Don't think that I'm forging the question. That is our question is here. The question is from here. Calculate the number of moles in Roman 1, and we are in Roman 3. In 100 centimeters cube solution B. But we know the concentration of solution B. We were given that. So to do it easy, we know B is 0.5 molar, meaning that the 0.5 is the number of moles in 1000 centimeters cube of hydrochloric acid. Now we will ask 100 centimeters cube will give us how many moles? And 0.5 moles of solution B is contained in 1000 centimeters cube. So we will ask 100 centimeters cube will contain how many moles, because this is the original HCl. So it is 100 times 0.5 divided by 1000, and this one is going to give us a 0.05 moles. 0.05 moles. The next question, calculate the number of mole of hydrochloric acid that reacted with X carbonate, X2 carbonate solid C. Now we want the number of moles that reacted with C. This is important now. We have the number of moles of 100 centimeters cube solution B, which reacted with C. And then we have prepared 100 centimeters cube. We have the number of moles in 100 centimeters cube. solution D. Now we subtract the number of moles of this D in 100 from 100B, and then we get the number of moles that reacted with solid C. Therefore, minus moles in 100 minus moles in 100 centimeters cube, solution D will give us the number of moles that reacted with the carbonate. So moles of HCl that reacted with C equal to moles in B, which is 0.05, minus moles in D 100, which is 0.0085, and that one will give us 0.0415 moles. Now we have the number of moles of HCl. This is the number of HCl that reacted with C, with the carbonate. But now we can get the number of moles of the carbonate from the relationship between the carbonate and HCl. Now we can write X2 carbonate react with HCl solution B in this to give us X chloride. Not the X, it means it has a variance of 1, therefore you cannot put anything here. So plus water plus CO2. But this X is twice here, so we put 2 here. And then the chloride here is twice, then we put 2 here. So it means that the ratio between the carbonate and HCl is 1 to 2. But we have the number of moles of HCl that reacted with the carbonate. We have the number of moles of HCl that reacted with C. The number of moles is 0, of HCl is 0.0415 moles. So we will ask 1, the carbonate will contain how many moles. Therefore you can see, because this one is 1 to 2, the number of moles of the carbonate is going to be a half that of the acid. So moles of X2 carbonate equal to a half times 0.0415, which is equal to 0.02075 moles. A half of that one. So the next question is calculate the relative formula mass of the carbonate, RFM. We want to calculate the RFM. So RFM, we know we can use this triangle. We know that moles RFM mass. Now we have the mass of the carbonate. Remember, we were given the mass of the carbonate. The mass of the carbonate is solid C is 2.2 grams. And we have the moles of the carbonate is this. So therefore we can get RFM. So RFM equal to RFM is equal to mass divided by moles. Mass is 2.2 divided by moles, which is 0.02075, and this one will give you, use your calculator, to give you 106. So the RFM of this carbonate is 106. Determine or calculate the relative atomic mass of X in the solid C. But we know now, since we have the RFM of the carbonate, it means that X2 carbonate equal to 106. So X, there are 2 of them, so we say 2X plus carbon, which is 12, plus oxygen, that is 16 times 3, will give us 106. 2x plus 60, because this is 48 plus 12, equal to 106. You like terms together, take this one there. 2x is equal to 106 minus 60. So 2x is going to give us 46. So we want the value of x divided by 2 divided by 2. So x is equal to 23. So the relative atomic mass of x is 23.
Right, welcome once again. Let me take you through practical chemistry paper 3, which was done October and November 2011. You are provided with 1.6 grams of solid A, a diabasic. Like I have always explained, a diabasic acid is an acid which has 2 hydrogens. An example is sulfuric acid. You should always know sulfuric acid is an example of a diabasic acid. Solution B contains 4.0 grams per liter. So solution B was prepared 4.75 grams in 1 liter. It is important for you to note that. And then aqueous sodium hydroxide solution C. So solution C is sodium hydroxide. Phenolphthalein indicator. You are required to prepare solution of A and use it to determine the concentration of sodium hydroxide. Solution C. React salt B with excess sodium hydroxide and then determine the relative molecular mass of salt B. Procedure 1, like I told you in a practical paper 3, the only thing you do is to follow instructions, especially in our setting. So you need to use to understand which solution is reacting with which. Right. So procedure 1, using a burette, place 25 centimeters cube of solution B in each of two 250 conical flask. Using a pipette and a pipette feeder, add 25 centimeters cube of solution C to each of the 2 conical flasks. Now here we are reacting solution C with B. And then you are being told that sodium hydroxide is in excess, is added in excess. Label the conical flasks 1 and 2. Heat the contents of the first conical flask to boiling and then let the mixture boil for 5 minutes. Allow the mixture to cool. Repeat procedure B with the second conical flask. While the mixture is cooling, proceed with procedure 2. Just following instructions is important in a practical paper. Let's go now. We assume we have done all that. Now let us go to procedure 2. Place all solid A in a 250 ml volumetric flask. Add about 150 centimeters cube of distilled water. Shake well to dissolve the mixed solid and then add water to make up the mark. Label this solution A. So we have remember solid A was a diabasic acid. Solid A was a diabasic acid. We have dissolved that solid and we have prepared solution A from solid A. The volume, total volume is 250. Very important to understand that. Part B. Place solution A in a clean burette. Solution A in the burette now. Using a pipette and a pipette feeder, place 25 of sodium hydroxide. Actually, solution C is sodium hydroxide in a 250 conical flask. Add 2 drops of phenolphthalein indicator and titrate with solution A. Record the results in the table below. So now in procedure 2 we understand very well. After preparing solution A, which is a diabasic acid, so an acid is going to react with a base which is sodium hydroxide, solution C. It is important to understand that way. So the volume of solution A used. Let me give you 19 or 29.7. Our initial rate will be 0.0, 29.7, 29.4, 0.0, 29.4, 29.3, 0.0, 29.3. You can see this 29.7, 29.4. This one is some of the afar, so it can lead us to getting inaccurate volume. Therefore, let us use these two because they are close. So 29.4 plus 29.3 divided by 2. The volume is 29.35 centimeters cube. That is the volume of solution A used. Calculate the concentration in moles per liter of the diabasic acid in solution A. So what you must always remember is that the diabasic acid, we were given 1.6 grams of the diabasic acid. We have been given the RFM of the diabasic acid, relative molecular mass. So moles of solution A in 250 centimeters cube, the one we prepared will be equal to, moles will be equal to mass of RFM, which will equal be 1.6 divided by 126, and this one will give us 0.01269 moles. So this is the number of moles of solution A. Solution A. But what was the volume of solution A we prepared? We prepared 250. We put the solid into a volumetric flask, 250, then we added 150 centimeters cube of water, then added water to the mark. Once it reaches the mark, it forms a volume of 250. Now, this is number of moles in 250. We have been asked to calculate the concentration in moles per liter. So we want the number of moles in 1,000 molality. So we will ask 250 centimeters cube of solution A as these moles. (1,000 centimeters cube of solution A will contain which moles? So it is 1,000 times this divided by this. That one will give you 0.05 moles. Very good. Calculate the number of moles, the moles of the diabasic acid used. The diabasic acid used. Right, so moles of the diabasic acid used, we know the acid we used, the volume, the total volume of A used, which is the diabasic acid, is 29.35. But we know the number of moles in 1,000 centimeters cube. So it is easier for us to get the number of moles that was used. We ask that 1,000 centimeters cube of A contains 0.05 moles. And then that was 29.35 centimeters cube of A will contain what number? So it is this times this divided by this. 29.35 times 0.05 divided by 1,000. So we give you 0.0014675 moles. 0.0014675 moles. This is the number of moles of A used. A is the diabasic acid. You need to understand that. Now calculate the number of moles of sodium hydroxide in 25 of the solution C. So sodium hydroxide is solution C, the number of moles. Remember 25 centimeters cube reacted with 29.35 A, right? So since we know that the acid was a diabasic, so when you write a reaction between sodium hydroxide with sulfuric acid, you know how the reaction occurs and how you should balance. We put it to here and then like that. So this one is sodium hydroxide reacting with A, which is a diabasic like sulfuric acid. It is going to form sodium A. But A will put 2 here because this one is the difference here is 2. The difference to sodium is 1, and then it will form water. So because of this 2, we put it 2 here. So that tells you that the ratio for the sodium and the A is going to be 2 to 1, right? So the number of moles of sodium hydroxide in 25 of solution A will be twice the number of moles of A will be twice. So moles of C in 25 centimeters cube equal to 2 times 0.001467.5, which is equal to 0.0022935 moles. I hope you are getting this point. Concentration of sodium hydroxide in moles per liter. Now we have the number of moles in 25 of sodium hydroxide solution C. What will be the number of moles in 1 liter? Molarity. In short, we want to calculate molarity. Molarity is the number of moles in 1 liter. So we say 25 centimeters cube solution C contains 0.02935 moles. 1000 centimeters cube of solution C will contain what? So it is 1000 times 0.002935 divided by 25, and this one is going to give you 0.1174 capital M. Procedure 3. Add 2 drops of phenolphthalein indicator to the content of the first conical flask prepared in procedure 1 and titrate with solution A. Record the results and repeat the procedure with the content of the second conical flask in test tube A. Now we are titrating solution A, which is the diabasic acid, with the content which was in the first conical beaker with the one that we prepared in procedure 1. We labeled it 1 and 2. The thing you need to understand is this, that we had sodium hydroxide in excess, which is going to react with B. It will react with solution B. Always remember this. What happened in procedure 1? C, which is sodium hydroxide, reacted with solution B. The excess sodium hydroxide, which was in excess, is now the one we are going to react with A, the diabasic acid, the excess sodium hydroxide. After solution 25, after sum of the 25 centimeters cube of solution C reacting with 25 of solution B, some sodium hydroxide remained, and whatever we are calculating on the procedure 3 is the excess sodium hydroxide solution. So after A reacting with excess sodium hydroxide, the volume of A that was used, that is the diabasic acid, is as follows. We use 11.5, 11.4. Let us have our initial at 0.0, 0.0. We have 11.5, 11.4. So the concept is, do you understand what's happening? Yes, A is reacting with excess sodium hydroxide. The solution sodium hydroxide that remained after reacting with B, solution B. So average of solution A, that is 11.5 plus 11.4 divided by 2, which is 11.45 centimeters cube. Calculate the moles of the diabasic acid used. We know the concentration of the diabasic acid. Remember the concentration of the diabasic acid. We know that solution A, the concentration of solution A was 0.05. This is the number of moles in 1,000 centimeters cube. So we will ask 11.45 will be what moles? Now we know that 0.05 is the number of moles of solution A in 1,000 centimeters cube. Then we will ask 11.45 centimeters cube of solution A. That is solution A. Solution A will contain what number of moles? It is this times this divided by this. 11.45 times 0.05 divided by 1,000, which will give us 0.0005725 moles. Calculate the number of moles of sodium hydroxide that reacted with the diabasic acid. We know this is the sodium hydroxide reacting with the diabasic acid. Therefore, the ratio of the sodium hydroxide with A is 2 to 1. So more, and this is the number of moles of the diabasic acid that reacted. So this one will be twice. So moles of C that reacted with A will be equal to 0.005 or 0.3 zeros 5725 times 2, which will be equal to 0.00145 moles. So this is the number of moles of the sodium hydroxide that reacted with the acid. Now we want to calculate the number of moles of sodium hydroxide that reacted with 25 solution B, right? So we need to understand that in our first procedure, let us look at the first. So from procedure 3, we have the number of moles. Procedure 2, 3 or 2 from procedure 2. We have the number of moles of sodium hydroxide in 25 solution A, which was 0.002945. So what we do, we subtract the number of moles that has reacted with A on the other side. So moles of sodium hydroxide that reacted with B is given by subtracting the original 0.0029314 minus this 0.001145, which will give us 0.0017864 moles. So this is the number of moles of sodium hydroxide that reacted with B. Given that 1 mole of salt B react with 2 moles of sodium hydroxide, so meaning that B and C, because this sodium hydroxide, the ratio is 1 to 2. But we have the number of moles of sodium hydroxide solution C. So calculate the number of moles of B. So it will be half the number of that. So moles of 25 centimeters cube B will be equal to half the moles of C, which is equal to 0.00 1786 the one we did in our previous Roman 3. So half of this is equal to 0.000008932 moles. Calculate the concentration in moles per liter of salt B in solution B. Now we have the number of moles of B in 25. So in 1,000 we will get 25 centimeters cube of B is 0.0008932 moles. We will ask 1,000 centimeters cube B will contain what? This times this divided by this. That one will give you 0.03573 capital. Yeah, that is the molarity of B. Calculate the relative molecular mass of B. Remember, RFM is equal to mass in grams per liter divided by molarity. Molarity of B we have here, and mass in grams of per liter of B we have. We were provided with that. The mass for per liter we will check what we were provided. So solution B was prepared by 4.75 grams per liter. We have that, and we have the molarity. So we will get the RFM. So the RFM is equal to 4.75 divided by 0.03573, this one, which will give us 132.9, which is the same as 133.0. You are provided with solid D. Carry out the following test and write your observations and inferences in the space provided. Place about 1/2 of the solid D in a test tube and heat it strongly. Test any gas produced with both red and blue litmus papers. Gas which turns red litmus paper blue is produced. The blue litmus paper remains blue. Yes, so when a gas is produced which turns red litmus paper to blue, that gas is a basic gas. Therefore, we use ammonium ion. To present that is present. Place the rest of the solid in a pouring tube. Add about 10 centimeters cube of distilled water. Shake well. To about 2 centimeters cube portion of solution, add about 1 centimeters cube of hydrogen peroxide and shake well. Hydrogen peroxide. To the resulting mixture, add aqueous sodium hydroxide, drop poison until in excess. So the observation is that a brown precipitate is formed. A brown precipitate which is insoluble in excess. Sodium hydroxide. So a brown precipitate is associated with the ion 3 positive present. Brown PPT insoluble in excess, ion 3 present. You are provided with solution E. Carry out the following test and write your observations and inferences in the spaces provided. Divide solution E into 2. To one portion of solution E in a test tube, add 3 drops of barium nitrate. Retain the mixture retain the mixture for use in test Roman 2. White precipitate is formed. White PPT is formed. We are adding barium nitrate, then definitely are present. The sulfate, the sulfite, and the carbonate are present. So the mixture, this mixture we retained here, add 5 centimeters cube of 2 more nitric acid. Yes, then the observation is that the white precipitate dissolves, forming a colorless solution. Right? And then, because we are adding an acid, we expect effervescence or no effervescence. That one always remember. So this one, effervescence occurs. So if it dissolves to form a colorless solution and the no effervescence occurs, that confirms that the sulfite and the carbonate are present. Yes. To portion 2 of solution E in a test tube, add 2 drops of acidified potassium dichromate 6 and warm the mixture. Then the orange turns green. The orange color changes to green. Or you can say the color change from orange to green. So if that happens, and we are in we have not entered into organic chemistry, and we have understood very well we are doing with inorganic, then it says, it confirms that the sulfite ions are present. The sulfite is the one which is going to be oxidized to form to be oxidized to sulfur 4. To sulfate. The sulfite will be oxidized by this to form, and then this one will change to green. Provided with that, place 5 drops of liquid F on a crane dry watch glass and ignite it. So the liquid burns with a blue non-sooty flame. Excuse me. So it is burning with a blue non-sooty, then it means it is a saturated organic compound. Saturated organic compound. But if this one disappears from your head, so you can say the alkane or alcohol present. You can use it this one or this present. Place about 2 centimeters scoop of F in a clean test tube and then add sodium hydrogen carbonate. Sodium hydrogen carbonate, there is no effervescence, because that's what we expect. There's no effervescence, then it means the alkanoic acids are not there, are absent. The alkanoic acids are absent. Lastly, place about 2 cm of liquid in a test tube. Add about 1 cm of acidified potassium dichromate 6 and warm the mixture. Then what happens is that the orange or the color change from orange to green, because now we are dealing with organic chemistry. Then that confirms that the alcohol is present. The alcohol is present. The alcohol is present. Welcome. Let us look at this chemistry practical, the year 2021, but this is the April 2021, meaning it was the exam for 2020. These are the students who were supposed to do an exam in the year 2020. So let us go in and see what they were provided with. You are provided with 5.3 grams solid A, sodium carbonate, solution B, hydrochloric acid. You are required to determine the molar heat of the solution of solid A, concentration of the hydrochloric acid, solution B. Procedure 1. Using a purette, place 30 centimeters cube of distilled water in 100 milliliter plastic beaker. Stir the water with a thermometer and measure its temperature after every half a minute interval. Record the readings in table 1. At exactly 2 minutes, add all of solid A to the water at once. Stir well and continue measuring the temperature of the mixture after every half a minute interval. Record the readings in table 1. Retain the mixture in the beaker for use in procedure 2. So want to use these values. Let us use 24. You can put 2.0 to 1 decimal place. 24.0, 24.0, 24.0. The reason why I'm putting 24 because this is you are measuring the temperature of this water at room temperature before you have added anything. So the room temperature could be 24, 23 depending on the weather that day. So up to this, now when the time is exactly 2 minutes, you can see 2 minutes where there is X. You add all the solid A at once. So from that now, the temperature will start rising or decreasing, it depends. But for this one, the temperature was decreasing. And we want to use, the first one was 31. After half an hour, the temperature rose up to 31. At the third minute, the temperature went to 32, and then 33, stood at 33, stood at 33, and then dropped to 32. So this is the trend, increase and then decrease. There you have all the table is filled. I used 1 decimal point. Please ensure if you use a decimal point, one of them, make sure that you use the decimal point constantly or consistently. So now this is our table. Here you expect to have 3 marks. On the grid provided, plot a graph of temperature, vertical axis against time. when you are told to plot a graph of temperature against, so against, the one which comes after the word against is always the x-axis. Time. X-axis comes after against, the word against, and then the vertical. They have also told you vertical axis. That is the y-axis. So this is temperature. So make sure you are convenient. You know how to put the scale, because if you put the other way around, you will not get the mark for labeling. So let us go straight and look at the graph. Now let us draw a graph. You take your ruler, you draw the y-axis. You draw the y-axis like that. Draw the x-axis. Draw the x-axis like this. After drawing that, label the x and the y-axis. We have been told to draw a graph of temperature, so we name here temperature. Temperature is always in degrees Celsius, and then against time. This time of ours is in minutes. So by doing that, you already have a mark. That's one mark for labeling. Now let us give it the scale. We will give here a 0. But remember, temperature, room temperature, we cannot have a temperature of 1, 2, 3 up to 10. So what we do, we can break this graph. We can break the graph so that we can have a reasonable temperature. So we can begin somewhere here at a temperature of, remember our range is 24 to 32. 24 to 32, therefore we can start here 23, right? And then 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, and 35. And 35. So we have now labeled the vertical scale which for temperature. Now let us go for time. Our time, we have a range of half an hour, half a minute. So from 0 we can have 1 minute at this point, and then 1.5, 2 minutes, 3 minutes, 4, and 5. So in between here, 0 and this is a half. This one will be 1.5, 2.5, 3.5, 4.5, and we have finished with the scale. Now we have already scored 2 marks. That is for the scale labeling, like that, choosing a correct scale that covers at least 3/4 of the graph. The next thing is now to plot the graph. When time was 0, our temperature is 24. So you should always remember this information here. When temperature is 0, when time is 0, temperature is 24. When time is a half, 24. When time is 1, 24. When time is 1.5, 24. So that is what we are doing. So when time is 0, the temperature was 24. So we put that point there. Another point here. Another one here. Another one here. Up to that point. Because at 2, there is nothing we did. We didn't take the temperature when time was 2. So when the temperature, and then from here we have 31. So at the 2.5 we have 31. So we go, where is 31? 31 is here. You put a dot there or an X. At 3, that is 32. At 3.5 we have 33. At 4 we have 33. at 4.5 we have 33, and then at 5 we have 32. Now this is a straight line. You draw a straight line from this point. I hope you are conversant with the graphs dealing with energy changes. These are the graphs. We have endothermic graph, exothermic graph. Those are the things you need to understand before you go to an exam room. So I have plotted these 2 points. This means that after you have this point, you extrapolate this point to this side, extrapolate where the 2 points are going to meet. That will give us the maximum temperature reached. So we extrapolate. You use now a dotted line like this, and then this side, dotted line. Very good. Now we want to read our maximum. For us to read the maximum temperature, we use a dotted line towards the y-axis. Don't worry about this. So this is at this point. So our maximum is 34 degrees Celsius. That is the temperature. Remember, let us also join this one, our room temperature. This. Now we are measuring the temperature between the minimum, this is the minimum, and the maximum here. This temperature here and here. This is what we are measuring. So let us go to the question. Determine from the graph the temperature change. So we have done from the graph. So how will you show that you have used the graph? You must extend this line. You must extend this line, and then from this, where the 2 lines meet, you go across like this with the dotted line. That will show that you used your graph. That's how you will get this 1 mark. So ours is 34 minus our initial, which was 24, and that one will give us 10 degrees Celsius, and that is the temperature change. Calculate the number of moles of solid A used. So to get solid A, you go back to what you are provided. We are provided with 5.3 grams of solid A, sodium carbonate. So we have the mass, and we have been given the RFM. So the mass of solid A, is 5.3. And the RFM is 106, but we know moles equal to mass over RFM, which is 5.3 divided by 106, and this one is the your calculator. That is 5, so it's off. 5.3 divided by 106. That one gives you 0.05. So we have 0.05 moles of the solid. Now question number 2. Calculate the molar enthalpy of solution and show the sign of the heat change. That is the enthalpy of solution. You show the sign. Assume that the solution density is this, and the specific heat capacity is 4.2. Now here, the first thing we calculate is the heat change. We know heat change equal to mass, capital M. This is the mass of the solution that was used. Remember, we measured 30 centimeters cube of distilled water in which we added solid A, and the temperature started rising. So the solution, the mass of the solution times the specific heat capacity times the temperature change will give us the heat change. Now this one, we measured 30 centimeters cube of distilled water. Remember, you should know that the density equal to mass over volume. Now the density of water is 1. The mass, we don't know. but we have the volume which is 30. So we multiply times 30 both sides. So x equal to 30 grams. Now this 30 centimeters cube is as good as 30 grams. Now we convert 30 grams to kilograms. So that is now 30 over 1,000. Now I've converted this to kilograms, and times specific heat capacity, which is 4.2, times temperature change, which we calculated, which is 10. Now this one, you take your calculator and it will give us 30 divided by 1,000 times 4.2 specific heat capacity, and then times 10. So that one gives us 1.26. So 1.26 kilojoules. Right? Now the next one, now we want to calculate the molar heat of solution. So how do we know that this is the heat that was produced by 0.05 grams of the solid A? So we say that 0.05 moles of solid A was able to produce 1.26 kilojoules. We want to know 1 mole of A would produce what amount of heat, because we want molar enthalpy. Molar means for 1 mole. So 1 times 1.26 divided by 0.05. This one gives you bring your calculator, this answer, and then divide by 0.05. That gives you 25.2. Now this one is 25.2 kilojoules per mole. But remember, the reaction was exothermic. The temperature was rising, increasing. Therefore, our final answer should be negative 25.2 kilojoules per mole. That is the correct answer. Thank you. Let us go to procedure 2. Procedure 2. Fill a puree with solution B. You should always remember, what was solution B? Solution B is hydrochloric acid. Solution B is hydrochloric acid. These are the information which you must put at the back of your head, at the back of your mind as you continue to go ahead. So fill the puree. In the puree, we are going to have HCl solution B. Transfer all this mixture in the 100 plastic beaker from procedure 1 into a 250 ml volumetric flask. Add distilled water to make up to the mark and shake. Label the mixture solution A. Using a pipette and a pipette filler, place 25 centimeters cube of solution A into a 250 centimeters cube conical flask. Add 2 or 3 drops of phenolphthalein indicator and titrate with solution B. Do not pour out the content of the mixture of the conical flask. Don't pour. So you need to follow instructions. That's why you are supposed to use 15 minutes first to read through the instructions before you start doing the practical. So and then record the table and then add 2 or 3 drops of methyl orange indicator to the content of the conical flask. Titrate the mixture with solution B and record the reading in this second titration table 3. Yeah, that is it. So the information I want you to understand is that we have 30 centimeters cube of sodium carbonate solution from procedure 1. We have put the solution into a 250 volumetric flask. We are adding water up to 250 centimeters cube. So we are going to prepare a solution of solution A, which is equal to 250 centimeters cube, right? That is the information you need to understand. So HCl is going to react with a carbonate. It's going to react with a carbonate solution. So that is correct. So let us see the what we are going to fill in the table. Let us use these values. 16.5, 16.5. Our initial is 0.0, 0.0, and then our arithmetic is 5.5. Sorry, 16.5, 16.5. So average volume of solution B used here. So now we have 2, so that is 16.5 plus 16.5 divided by 2, which will give you 16.5 centimeters cube. Table 2, you will give you the same value, 16.5, 16.5, 0.0, 0.0, and then 16.5, 16.5. Remember, this value doesn't matter, but if you can pick just this value n and use it appropriately, step by step, you are going to score a lot of marks, and you only miss some accurate mark, which is 1 mark. But I don't recommend that you don't do the practical, but I'm saying that this value here, the average, it doesn't have much. The thing is, do you know how to use that value, the average you have decided to use, correctly, step by step, down the questions? The average here is going to be 16.5 plus 16.5 divided by 2, and we have 16.5 centimeters cube. So this is how the table was. So let us go to the next page and see the questions. Calculate the concentration in moles per liter of sodium carbonate solution A. Right? But what was solution A? Remember very well, solution A is a solution that was made by dissolving 5.3 grams sodium carbonate in water, right? To make a 250 centimeters cube. We have been given RFM. We know how to calculate the moles, isn't it? So we can say, now let us get the number of moles in 250. So moles, we know that moles equal to mass divided by RFM. RFM is 106, which will give us 0.05, right? This is the number of moles of sodium carbonate in 250 centimeters cube, because our solution was made in a 250 volumetric flask. Therefore, this is the number of moles in 250. So, concentration in moles per liter. We want the number of moles in 1 liter. So we will ask if 250 centimeters cube of solution A has 0.05. We will only ask what will be the number of moles in 1,000 centimeters cube of solution A. So it is 1,000 times this divided by this, which is going to give you 0.2 capital M, or 0.2 mole per dm cube, mole per liter, mole per liter, mole per liter. That's one way you can do it. I want to do it in a different way. Another person can say like this: we know that the 5.3 grams, these are the number of moles that are in 250 centimeters cube. So we say 5.3 grams is in 250 centimeters cube, isn't it? Yeah, remember from the procedure, there are some things which you need to put in your mind. We dissolved solid A in 30 centimeters cube from procedure 1. That solution, we put it into a volumetric flask. Then we add water to 250. So the number of moles, or the mass in 250 is 5.3 grams. The one we used, right? So we will ask if 5.3 grams is in 250, we will find out what will be the number of grams, or the mass in 1,000. It is this times c divided by this, which is going to give us 21.2 grams per liter. This is now the mass in grams per liter. But we know, how do you calculate molarity? We know what is molarity. Molarity is the number of moles in 1 liter. Molarity equal to mass in grams per liter divided by RFM. We have mass in grams per liter, which is 21.2 grams per liter. And then we have RFM, 106 divided by 106. And this one gives you 0.2 capital M. Capital M stands for molarity. Capital M stands for moles in 1 liter. Thank you. So the essence of doing it like this, or to giving it two alternative, that's why I'm doing this. I'm not doing it. I want you to get the understanding, to understand molarity, to understand moles, how to calculate moles, to understand mole concept. That is my task. That is my endeavor. So calculate the number of moles of sodium carbonate in 25 solution A. Now we have the number of moles in 1 liter. We also have the calculate the number of moles of sodium carbonate in 25 centimeters cube of solution A. But now we have the number of moles in 1 liter. That is, this is the number of moles of solution A in 1 liter. Then we ask, what will be the number of moles in 25 centimeters cube of solution A? So we say 0.2 capital M means number of moles in 1000 centimeters cube of solution A. Then we ask 25 centimeters cube solution A will contain what moles? 25 times 0.2 divided by 1000, which will give you 0.0125 moles. Calculate the number of moles of hydrochloric acid in the total volume of V1 and V2. The total volume. Now remember, V1 we used 16.5 and V2 was 16.5. So the total volume, our total volume will be 16. So total volume we would be 16.5 plus 16.5, which is equal to 33 centimeters cube. That's our total volume. Solution B. But we don't know the number of moles of solution B. There is no much information we have for solution B. Remember, solution B, the only thing we know about solution B is just that you are provided with solution B, hydrochloric acid. But since now it has reacted with the carbonate, we can get the number of moles there. So sodium carbonate will react with HCl, giving us sodium chloride plus CO2 plus water. But we will balance, because these 2 here, we will put 2 here, we put another 2 here. So the ratio for the carbonate and HCl is 1 and 2. Right? But we know the number of moles of the carbonate from here, the number of the carbonate that reacted with this HCl, the degree of it. So if with this number of moles is 0.01, this one, to 5, then the number of moles of HCl will be twice, because the ratio is 1 to 2. So moles of HCl in 33 centimeters cube that reacted with the carbonate equal to twice. 2 times 0.1 0.0125 125, which is equal to 0, 0.0. What is that? Let us use the calculator kindly. So answer times 2, answer times 2, which is equal to 0.025 moles. So this is the number of moles of HCl in 33 centimeters cube that we also used. Roman 4. Calculate the concentration in moles per liter of hydrochloric acid in solution B. Concentration in moles per liter. Concentration in moles per liter means number of moles in 1 liter. Molarity. It means molarity. But we know that the 33 centimeters cube of solution B has 0.025 moles. Then what will it be 1,000 contain? So 0.025 is the number of moles contained in 33 centimeters cube solution B. 1,000 centimeters cube solution B will contain how many moles? 1,000 times 0.025 divided by 33. That one is going to give us 0.7576. Capital M. Capital M stands for moles in 1 liter, molarity. Now allow me to take you through the qualitative part of it. You are provided, that's question 2, you are provided with solid C, carry out the following test, write the observations and inferences in the spaces provided. Place all solid C in a boiling tube, add about 20 centimeters cube of distilled water, and shake until all the solid dissolves. Label the solution as solution C. Use about 2 centimeters cube of solution C in a test tube for each of the following tests. A. Add aqueous sodium hydroxide dropwise until in excess. This is now where the students go wrong. When you are told to add dropwise until in excess, what it means, first, use 2 drops, make the observation, see what will happen, and then afterwards, add the sodium hydroxide in excess and then make another observation, because here you are expected to make 2 observations at once, simultaneously. So this is what was observed. White PPT. So this is the first observation. When you put a drop, a white PPT is formed. Then what happens when the white precipitate, when the sodium hydroxide, what happens to the white precipitate when sodium hydroxide is added in excess? The white precipitate is formed, which now make form for the excess, which dissolve, or which is insoluble, which does not dissolve in excess. In excess sodium hydroxide. So this is the expectation. Whenever you are asked to add sodium hydroxide dropwise and then in excess, then you should first use the 2 drops, make the observation, and then add in excess, make the observation. So a white PPT is formed which is insoluble, which does not dissolve in sodium hydroxide, meaning the white precipitate remains, persists. So if that is the case, then what is present? What is present is that calcium, 2 ions, magnesium, 2 ions, and barium, 2 positive, are present. If the white precipitate dissolve to form a colorless solution, then we know the amphoteric ions are there, aluminium, lead, and zinc. But since this one it is insoluble in excess, it means that the calcium ions, magnesium ions, and barium ions are present. Now you can ask me, is it correct for you to write that lead 2 positive, aluminium 3 positive, and zinc 2 positive absent? It is correct, but unacceptable. This is correct, but nowadays they don't accept that. If it is not there, then tell us what is there. That's why I've given you what is there. Now you know, whenever this happens, what is there is calcium, magnesium, and barium. If it happens otherwise, the white precipitate dissolve to form a colorless solution. Write this and this and this present. Don't write this and this absent. Write what is there. Thank you. Add 3 drops of aqueous sodium sulfate. We are adding sodium sulfate. So you are seeing the sulfate. Here we expect, because remember all salts of sodium are soluble. So we are going to expect that this one, if it gets into that solution in our test tube and finds lead, 2 ions, it will form a white precipitate. If it finds barium, it will form a white precipitate. If it finds calcium, it will form a white precipitate. The sulfate. We know salts of sulfates which are insoluble, which forms white precipitate. So what was the observation for this one? White precipitate is formed. So if a white precipitate is formed, but from the if you put that lead is present, then you are contradicting yourself, because initially in our previous inference we said lead is not there. So you don't, where will you get it from so that you can put it here? Therefore you don't add that here because it was not there initially in the previous observation. Therefore here it is only calcium and barium that are present. Calcium 2 ions or barium 2 present. Barium nitrate. Whenever we are adding barium nitrate, we expect a white precipitate, because barium will form barium sulfate, barium carbonate, barium sulfite. These are the 3 salts or anions that will form a white precipitate with barium. But now, since there is no white precipitate, then it means the sulfate, the sulfite, and the carbonate, they are absent. They are not there. Otherwise, if they were there, barium would form a white precipitate with N of them. Add 3 drops of aqueous lead 2 nitrate. Lead 2 nitrate. Heat the mixture. We have been asked to heat the mixture. Heat the mixture. Then this is the observation. A white precipitate, white PPT formed. The observation we have made is for adding red to nitrate. After heating, what happened? Did the white precipitate dissolve on heating or it did not? That is the second observation. A white precipitate is formed which dissolve on heating. So that tells you, if you are adding this, then it means a chloride was there. A chloride. So that it forms lead chloride. Red chloride is the only salt which forms a white precipitate, and when warmed or heated, it dissolves to form a colorless solution. But is it only chloride? You can also use bromide ions. So bromide ions and the chloride ions will behave in a similar way, because actually they are halogens, you can see. So these two will behave like that. So you say this or this is present. and you get your marks, all of them like that. Let us go to the last bit of it. You are provided with an organic compound. Very important. You have been asked, you have been told, you are not going to find out whether it is an organic. This one you have been given straight that it is an organic compound. Solid D. Carry out the following test, record the observations and inferences in the space provided. Describe the appearance of solid D. It was a white crystal, therefore you say white crystalline solid. Or you can say that's all white crystals. You can say it is white crystals because the salt was white. Divide solid D into 4 portions. Yes. Place the first portion of solid D on a watch grass and burn it with a Bunsen burner flame. Then what happened? Remember, it is a solid, so the solid melt and burns with a yellow sooty flame. The solid melts, solid D melts and burns with a yellow sooty flame. Now we want to know whether it is a saturated organic compound or unsaturated. If it burns like this with sooty yellow, then that tells you it is the unsaturated, the double bond, or the triple bond. Present. It is acceptable for you to say unsaturated organic compound present. It is acceptable to say unsaturated organic compound present. It is acceptable. Place the second portion of solid D in a test tube. Add about 3 centimeters cube of aqueous sodium hydroxide. Now you see, here we are using aqueous sodium hydroxide. Basically, we want to test whether this organic compound is basic, is neutral, or is an acid. Because if it is an acid, it's going to produce effervescence. That's why we are using a base. We basically want to test whether it is an acid. Yes. So let me give you the observation. The solid dissolve, solid D dissolve in sodium hydroxide, then it dissolves in sodium hydroxide, forming a colorless solution. Now remember, a solid is dissolving in sodium hydroxide, which is a base. Then that one definitely tells you that this solid was acidic, right? Yeah, an acid plus a base, it will give you a colorless solution, neutralization reaction. But now we are dealing with organic chem. Here we give the inference of organic acids. It is acceptable for you to write that acidic organic compound present compound. Acidic, it is acceptable. But also, if you don't remember this, you can write that the functional group of alkanoic acids is present. It means that alkanoic acids are present. One of them is present. Number 3, place the third portion of solid D in a test tube. Add about 3 centimeters of distilled water. Heat the mixture and add 3 drops of acidified potassium manganate 7. Acidified potassium manganate 7. Then the observation is that the color, this one is decolorized, so you just say acidified potassium manganate, permanganate, that is, solution is not decolorized. We have reviewed that it did not decolorize. So another person can say the purple acidified potassium permanganate remains purple because it did not change. We know this one is purple. So if it doesn't change, then it means that the double bond, the triple bond, or the alcohol ROH was absent. Yeah, is absent. If this were present, the acidified potassium manganate would be decolorized. It could change from purple to colorless. But now it did not. It didn't do that. Therefore, it means that these three are absent. They are absent. Finally, place the fourth portion of solid T in a test tube. Add about 3 centimeters cube of distilled water. Heat the mixture and add all the solid sodium hydrogen carbonate provided. Then effervescence occurs. That now confirms actually that solid was an acid. Effervescence occurs. Carbonate plus an acid, we always expect carbon dioxide to be produced, therefore effervescence will occur. That confirms that the alkanoic acid are present. Okay, H. The alkanoic acid are present. It is you are provided with 2 grams of substance A labeled solid A. Solution B, which is 0.05 molar hydrochloric acid, methyl orange indicator. You are required to determine solubility of substance A in water, relative formula mass of substance A. I want to take you procedure 1 because we need to understand here for us to go to procedure 2 because they are related in one way or the other. Place 200 centimeters cube of tap water in a 250 ml beaker and keep it for use in step 4. Actually, practical is to use just to listen and execute the instructions. Now this one, we keep it for Roman 6. Place all substance A in a dry boiling tube. That is the next thing. Using a purette, measure 10 centimeters cube of distilled water and add it to the substance A in the boiling tube. While stirring the mixture in the boiling tube with a thermometer, warm the mixture using a Bunsen burner until the temperature rises to 65 degrees Celsius. Stop warming the mixture. Allow it to cool while stirring with the thermometer. When the temperature drops to 60 degrees Celsius, start the stopwatch. Place the boiling tube in the beaker with tap water prepared in step 1 above. Continue stirring and record the temperature of the mixture after 2 minutes. Then thereafter record the temperature of the mixture after every 1 minute interval and complete the table. This is my way. I want us to retain the mixture with the thermometer inside for use in procedure 2. So I want us to understand here. What did we do? We took solid A, put it in 10 centimeters cube of water, and it is dissolving. that using the temperature here. I want just to give you the values so that you can draw that graph at home. So the values, this one I call it 6.0, 36.0, 30.0, 29.0, 27.5, 27.0, 27.0, 27.0, 26.0, and then 23.0. So draw that graph and you will see, you will be able to answer the question thereafter. Procedure 2. Using a panel, transfer all the mixture obtained from procedure 1 into a 250 ml volumetric flask. Rinse the pouring tube and the thermometer with about 20 centimeters cube of distilled water and add the rinses into the volumetric flask. Repeat rinsing 2 more times and add about 100 centimeters cube of distilled water in the volumetric flask. Shake until the solid dissolves. Add more distilled water to the mark. Label this solution A. So up to that point, I want to help you understand one thing, that from procedure 1, we add 30 centimeters cube of distilled water, dissolving solid A. So we are transferring 30 centimeters cube solution which is containing solid D into a 250 ml volumetric flask. So here we are going now to prepare solution A, which is 250 centimeters cube solution A. Very important to understand that. Leave around the more words, the procedure there, but the final thing we have done is we have prepared the solution A, where in 250 centimeters cube solid A. Thank you. Fill the puree with solution A. Using a pipette and a pipette filler, place 25 centimeters cube of solution B into a conical flask. Add drops of indicator provided and titrate using solid A. Now we are now titrating solution A against solution B, but we know what is solution B from our from solution B is 0.5 molar hydrochloric acid. Now that one we know. So A is going to react with B in procedure 2. So I hope you must understand the procedure. This thing here. Which solution do we have in the puree? Which one are we pipetting? We are pipetting 25 of solution B. Solution B, which is HCl. And then the solution which is in the puree. The solution in the puree, because we are told fill the puree with solution A, the one we have prepared. So the volume we are going to get here, the average volume is for solution A. That one is important for you to understand. So let us use this average volume. We want to use 30.8. 30.8. Our initial, I want to say to, can it is okay if you start at 0.0, 30.7, 0.0, 30.7, 0.0, do the arithmetic, 30.8, 30.7, 30.7. Because I can see this one the same, because I want very accurate answer, then I will do the average with the 2, leave this one outside. So the average is 30.7 plus 30.7 divided by 2, because I have done on with only 2. If I did all of them, I will divide by 3. This one will give me 30.7 centimeters cube. That's my average. Determine, remember, calculate the number of moles of hydrochloric acid solution B. Very easy. Why is it very easy? We know the molarity of solution B, 0.05 capital M. This is solution B. But we know, what does this mean? This means that 0.05 is the number of moles in 1000. But what was the volume of solution B used? We come back. Using a pipette 25 centimeters cube of solution B. So we will ask, this is 25 is the solution that was used. So we ask 25 centimeters cube will contain what number of moles? So this times this divided by this. That one will give you 0.00125 moles. Right, given that 2 moles of the acid reacted with 1 mole of solid A, calculate the number of moles of substance A used. Now, substance A, we have been given that A to B. This is substance A, this is the acid, HCl. So we have to do that, given that the 2 moles of the acid B, so 2 moles of the acid reacted with 1 mole of A, 1 mole. So the ratio is 1 of the acid and to the base is 1 to, or to 1, whichever way. So calculate the number of moles of substance A, but we know the number of moles of B. B is equal to, what will it be? 1. It will be a half. So moles of A in 30.7 centimeters cube equal to a half times 0.00125, which is going to give you 0.000625 moles. Moles. Calculate the concentration of solution A in moles per liter. Concentration of solution A in moles per liter. Moles per liter, that one simply means molarity. Molarity is the number of moles in 1 liter. So we are calculating molarity. But what do we know? We know this. We know that 37.7 grams of A contains this number of moles. So what will 1000 contain? We say that 30.7 centimeters cube contains 0.0000625 moles. Then 1000 centimeters cube of solution A will contain what moles? So it is 1000 times this divided by this, and it is going to give us 0.02036 capital M. Now this is molarity. Because it is molarity, I want us to give it to 2 decimal places. 1, 2. Because this one is a 0, let us take it to 2. If it is molarity, always try to make it up to 2 decimal places. 2 decimal places, it is fine. So this one we will truncate and say 0.02 capital M. For molarity, it is acceptable we use 2 decimal places. Okay, because this one can make a very big difference. This one, a very big one. So we round off. Calculate the solution concentration of solution A in grams per liter. Grams per liter. That one is very easy. And why is it very easy? We go back to what we were provided. We check what was the mass that we are given. So we were given the 2 grams of solid substance A. We were given 2 grams. But remember, we have prepared substance A or solid A. We have dissolved it in 250 centimeters cube. So we want mass in grams per liter. Grams per liter. So if 2 grams is in 250, 1,000, which is 1 liter, will be what? That's what we want to do. Two grams was dissolved to form 250 centimeters cube in the volumetric flask. 1,000, that is 1 liter, centimeters cube, will contain how many grams? So it is 1,000 times 2 divided by 250, which will be 8 grams per liter. 8 grams in 1 liter. Next question. Calculate the relative formula mass of A. We want to calculate RFM, relative formula mass. Always remember this triangle verse, which says that molarity RFM mass in grams per liter. So we want to calculate RFM. How can we calculate RFM? RFM is equal to mass, so RFM equal to mass. You hold this one constant, mass in grams per liter divided by molarity. Mass in grams per liter, we have grams per liter, 8. What was the molarity of solution A? Here it is. Concentration, molarity is 0.02. 0.02. So you use your calculator and you get it is 400 grams per mole. 400 grams. So the RFM is 400. Quickly, let me take you through the qualitative part of it. We have been given solid C. So let us see. Place all solid C in a boiling tube. Add 15 centimeters cube of distilled water and shake until all the solid dissolves. Use 2 centimeters cube portion of the solution in a test tube for each of the following tests A up to F. A. Add aqueous sodium hydroxide dropwise until in excess. Let me give you the observation that was there then. White PPT insoluble. White PPT which does not dissolve in excess. I have always told you, once you are adding sodium hydroxide, a white precipitate is formed which does not dissolve in excess. Then be sure magnesium ions, barium 2 ions, calcium 2 ions are present. That one you are sure of that. Next, add aqueous ammonia dropwise until in excess. Aqueous ammonia until in excess. Now, this time around there is no white PPT. No white PPT formed. If there is no white PPT formed, and we suspect that these ones were present, this one forms a white precipitate with ammonia. This one forms a white precipitate with ammonia, but this one does not. Calcium ions does not. Therefore, it means that calcium 2 positive is present. C. Add 2 to 3 drops of solution D. Aqueous. Add 2 to 3 drops of solution D. Aqueous sodium carbonate. Retain the remaining solution D, retain the remaining solution D for use in question 3. Right. So we are adding aqueous sodium carbonate. Sodium carbonate. So sodium carbonate is so we expect when it goes there, if there is calcium, it will form calcium carbonate. So here, what was the observation? White PPT. So if a white PPT is formed and there is no effervescence, actually there is no things of acid, because from here we have not seen there was an acid, something like that. So here we are going to just repeat that 2 positive are present, calcium, because the carbonate will form calcium carbonate, which is a white precipitate. That is the knowledge we are talking about. We are adding dilute HCl, 2 drops. And then, remember here, we expect effervescence. But why are we expecting effervescence? If there was a carbonate, isn't it? If there was a carbonate inside it there, because we have said calcium carbonate, it will form effervescence. But in this case, there is no effervescence. Oh, there is no effervescence. If there is no effervescence, it means that the carbonate, the sulfite, are absent. The carbonate and sulfite are absent. Add 2 to 3 drops of aqueous barium chloride. Barium chloride. Barium chloride. So barium chloride will form a white precipitate with the sulfate, with the sulfite, and with the carbonate. But we have said the sulfite, the carbonate are not there in from E, from the previous. We have said this one are not there. So if there is no white PPT, no white PPT. So what has remained? We are not going to we will not repeat this one. Yet on the previous one we have said they were absent. So you don't have to include them here. Here you only give the one which is remaining. Absent. This with this is a white precipitate. So there is no white precipitate. This one is absent. We are adding lead nitrate, then a white PPT formed. A white PPT is formed. That confirms that there is a chloride ions inside. Chloride ions. You can also say bromide ion present. Thank you. Subscribe and share. Thank you.